All right, so let's start our today's seminar, and we are glad to have Justin Hilburn from the Perimeter Institute, and he will speak about two categorical three-dimensional mirror symmetry. Justin, please.
Okay, so I'm hoping that this is going to be a pretty informal talk. So I hope that you guys interrupt me a lot. Basically, like in these days of Zoom seminar, it's kind of hard to feel connected. So the more you interrupt, the happier I'll be. Okay, and I just want to say that this is joint work with Ben Gammage and Aaron Mazel-Gee. And then I just want to especially, so this is math that's coming out of physics. And like sometimes like the physicists who are early on these things, like don't get all the credit they deserve. So I just really want to thank Matt Volibor, Tudor Demofte, and Davide Gaiotto for teaching me about 3D n=4 theories, especially when writing my first paper with them. Because in some sense, this is basically like a proposal that's like kind of it's hidden in like an appendix of that paper that I've sort of managed to make into math. So let me just go ahead and start with just some context for like the kind of thing that I'm trying to do. So people are all very familiar with Witten's formulation of mirror symmetry, which is that there are these certain kinds of quantum field theories, 2D n=2, 2, to be specific. So this is basically referring to the dimension of space-time, and this n=2, 2 is telling you like how much supersymmetry they have. And like one like special like kind of such a theory is like the Calabi-Yau sigma model. And that's basically the theory that has like a single bosonic field, which is a map from some two-dimensional space-time or some Riemann surface into your Calabi-Yau manifold. And these kind of quantum field theories are very, very special. They admit there are two ways of producing a topological quantum field theory from the supersymmetric field theory. One of them is called like the A model, and the other one's called the B model. And these are, very famous in mathematics. And the way that these sort of work is that you choose some sort of a supercharge inside of the supersymmetry algebra. So by that, I mean like an odd element of the supersymmetry algebra that squares to 0. And then this A twist, like you look at the fields such that QA, this A-type supercharge, is equal to 0. And like this ends up like putting some conditions on this field sigma. Basically, it says that like it's got to actually be holomorphic. And then moreover, there are some fermions in this model. And this thing tells you that when you're looking in like higher codimension, that basically you should be looking at like de Rham cohomology of various kinds of moduli spaces of holomorphic maps, which we all know very well. And then similarly, like in the B twist, looking for the solutions to QB = 0, this basically causes this field to be constant. So basically people usually tend to not even notice that there is a map from a 2-manifold in the 2DB model, because it's just a constant map. And then again, like there's some condition about the fermions, and this thing tells you that you study Dolbeau cohomology of these kind of moduli spaces, and that's what leads to things like coherent sheaves showing up. And there was this amazing formulation due to Kontsevich called homological mirror symmetry, which says that these TQFTs, like a priori, they're some sort of like very complicated mathematical objects, but actually like all of the information that is inside of these QFTs is actually determined by their categories of boundary conditions. So in this case, those are the Fukaya category and the category of coherent sheaves. And if you want to like understand mirror symmetry, which is some auto equivalence of the space of supersymmetric quantum field theories that exchanges A models, an A model of one theory with the B model of its mirror, then you should just think of that as being some sort of equivalence between the Fukaya category of X and coherent sheaves on the mirror space. And then like everything else is in there. And so this 3D mirror symmetry, like we're playing like the exact same kind of game. So there's some sort of a three-dimensional supersymmetric quantum field theory. And so here, like our canonical example is a hyper-Kähler sigma model. And so here, because we're in 3 dimensions, our field is a map from a 3 manifold into our hyper-Kähler target. And then again, inside of this supersymmetry algebra, we have 2 supercharges, an A-type supercharge and a B-type supercharge. And to get the corresponding topological quantum field theories, you look at the solutions for where this thing is 0. And again, this thing like produces some sort of PDEs for you. And so in this A model, this thing produces the Futter equation, which basically tells you, it's actually also coincides with the 3-dimensional Euclidean Dirac equation in this case. So this tells you that your field sigma satisfies the following PDE. So suppose like I'm studying things on R3, then you can study the PDE I times ddx plus j times ddy plus k times ddz applied to sigma is equal to 0. And then again, this equation like doesn't make, can still see like the interesting structures about M3. And so in order to make this topological, you end up taking de Rham cohomology of these kind of moduli spaces again. And again, this comes from something about the fermions. And then similarly, there's like another B-type TQFT, which is called Rozansky-Witten theory. And like, again, like this is just a theory of a constant map. So again, like usually when people study Rozansky-Witten theory, they don't think about this map from the 3 manifolds at all. And here you end up taking like Dolbeault cohomology of various moduli spaces related to this.
So just ask you a question. For this 2D n equal 2,2 theories, so some of them are massive, but with the Calabi-Yau target, they are kind of expected to be super conformal. So here you also, as an example, take hyper-Kähler sigma models, but
yeah, you usually want like a permuting, so you have like this sphere of complex structures, and usually you want an action of unit quaternions.
Yeah, but hyper-Kähler, it's sort of an analog of Calabi-Yau. But I can consider in 2D, consider massive models, then it will be duality, again, A and B, but one of them will be sort of Landau-Ginzburg. It's not quite Fukaya category in mathematical terms. So here in 3D, is there an analog, or do people consider this massive analog of massive 2-dimensional theories?
Yeah, you actually got ahead of me. So in fact, like those are going to be the main examples of interest. The reason being is that when we study mirror symmetry, it's very rare that like 2 sigma models will ever be mirrored to one another. And like the most natural statement is like massive sigma model. And so, yeah, if you want to know like what it is to be massive, like roughly, like you can add basically like a U1 isometry of Y, or like equivalently, you could add like the hyper-Kähler moment map.
Okay.
So this is like the analog of like the mass term. And I'm not going to talk about this at all, but the real dream of this sort of theory would actually be to do some kind of an algebra of the infrared type thing in 3 dimensions to study these. And so like I've been talking with like Davide and Hassan Khan about doing this, but we're not very far. But anyway, that's way ahead.
And there will be some probably combinatorial objects in infrared similar to these webs of Guyot-Morin-Witten or something like that.
Yeah, absolutely. But I'm not going to do that today. But
okay,
that's the dream.
Okay.
Yeah. So anyway, so this is the yeah. So these are like the when you add the symmetry, this is like the analog of like a Landau model. Okay, so let me then say that like there ought to be a two-categorical 3D mirror symmetry program where one produces categories from the A model and from the B model, or sorry, produces two categories from each of these things, and that you show that they're isomorphic when you have mirror hyper-Kähler manifolds. But like as I just mentioned, basically this is going to end up being too simple of a formulation. Like there's almost no cases where sigma models are dual to other sigma models. So you're basically going to be forced to consider gauge theories and like massive things, unfortunately. So this won't be quite as nice as mirror symmetry. Okay. So let me just like say some things about what is known about these two categories, although I'm not going to follow anything about the approach that I'm going to tell you right now. So let me just go ahead and assume that my choose a complex structure on Y, and let me just go ahead and assume that it's an exact holomorphic symplectic manifold. This is necessary to define the B-twist. And it's known that there are some especially nice objects that are going to be in this category. Basically, there are certain supersymmetric boundary conditions for the 3D theory called n equals 2, 2 boundary conditions. It's not that important. And the important thing about them is just that they're compatible with both twists. And one can actually try and study like what sort of boundary conditions are allowed by like rewriting your 3D theory as a 2D theory into a path space, just using like the Halm tensor or the Halm product adjunction. And when you do this, you end up getting some sort of infinite dimensional target, which is some space of maps from the interval into my holomorphic symplectic manifold. And then they have to have some kind of boundary conditions, and we'll be able to figure out in a minute what sort of properties these boundary conditions have to have. And then there's like a superpotential on this space, which is basically a holomorphic version of the symplectic action. So basically you can pull back your your complex Louisville-1 form along your map, and then integrate over the interval. And then you'll need to add some extra terms at the boundary in order to cancel some boundary terms when you want to do integration by parts. And like if you like look closely at like what happens when you do this, things work exactly like in the when you're studying the ordinary symplectic action functional. You find that what you need in order to study the variation of W is that you need that the complex Louisville-1 form restricted to each of your L0 and L1 are both D of Fi, these functions that I've added. And so in particular, that tells you that your Li are actually exact holomorphic Lagrangians. So those are like some particularly nice objects that we definitely expect to be around. And then one can actually use this this infinite dimensional LG model to try and compute the Halms. So basically, this is some infinite dimensional Kähler manifold with a holomorphic function. And so you can say that their Halms in the 3DA model between these two Lagrangians are actually just going to be this Vyas-Setter category of this infinite dimensional space with this superpotential. And there was a talk in the M seminar earlier this year where there was a great paper by Doan and Reshikov that was discussed. I think Doan was the one who gave the talk. And what he proved is that in the case that you have a cotangent bundle and your Lagrangians are graphs of functions or graphs of D of a function, then this Fukaya-Seidel category of this infinite dimensional space actually just reduces to the Fukaya category of the base with the superpotential given by the difference of these two functions. So yes, if you want to compute the Hom between the graph of two one-forms, it's just the Fukaya-Seidel category. And this should look very close to a, and I'm actually not sure like who to attribute this proposal to. Like basically this is like pretty old. It's like definitely like in a paper that we wrote, but I'm 100% sure that we weren't the first people to think of it. I think a lot of physicists knew this, but nobody could prove this. Anyway, but on the B side, there's like a similar result, which is well known due to Kapustin-Rozansky and Saulina, where they showed the same thing, that if you take the Hom between two Lagrangians in the B model, then it's matrix factorizations of this infinite dimensional space with this holomorphic superpotential. And in this special case where you're looking at the cotangent bundle and graphs of one forms, then this thing actually just reduces to matrix factorizations. And this is basically some sort of like a NOR, infinite dimensional NOR periodicity type reduction. But anyway, so you get this like very nice symmetry that when you're taking Homs between graphs of one forms, and the A model you get Fukaya-Seidel categories, and the B model you get matrix factorization. Okay, but let me just point out, we're going to see in a minute that unfortunately these Lagrangians are not enough in the A model. Basically these graphs of one forms. And the key computation that's going to tell us this comes from a result of Teleman. And actually, I'm going to like clear these pages, and then I'm going to like do this computation slowly because it's like the page is kind of a mess. And like this is a computation that I think I should write out very slowly. So let me just go ahead and like say like what Teleman was doing. So the key example where somebody actually knows how this works is in the case where we have a torus, T equals C star to the N, and we have pure T gauge theory. On one side, and the 3D mirror is given by the sigma model into T star of the Langlands dual torus. And Teleman was able to describe these categories in like a purely combinatorial way. And that's like very good. And one thing that I like to do is you can think of gauge theories as just being sigma models into stacks. So I'm going to think of this as being a sigma model into T star BT. It's just helpful, like basically to unify the two cases. All right, and so let's try and think about like what the A model might be. So Teleman's proposal is
the T star means the cotangent bundle or
cotangent bundle.
Maybe stack.
Here it's just cotangent bundle.
Here. Okay.
Yeah, so here these two are cotangent bundles. These, yeah, I guess maybe I shouldn't have called let me call my torus G then, just to make our lives, just so that this isn't an issue.
Yeah, that's good.
Doesn't make any difference to me. All right, so let's try and think about like what the A models could be, or what Teleman says that they are. And like one can think, and so let's start with like the sigma model side, because I think that that's like a little bit easier. And like what Teleman wants to do is he wants to like think about kind of like categorifying ordinary mirror symmetry. And so his ansatz is basically like, okay, well, we know that the Fukaya category of, say, T star S1 is nothing but local systems on S1. So maybe like the 3D A model for T star of C star, or generally T star of some torus, like maybe that's just going to be some like higher version of local systems. And so he makes this like very interesting ansatz where he decides that like that this A model should be the category, or the two category of categorical local systems. And these have like the following definition. Like you can just think of any topological space. Oh, sorry. You can think of like any algebraic variety just as being like a topological space. And any topological space, like you can think of as just being like a very special kind of infinity category, just an infinity category where all of the one morphisms are invertible. So he says, well, why don't we go ahead and look at the functions inside of the space of one categories from this torus G to the L into the one category. Oh, sorry, this would be in two categories. Into the one category of, sorry, into the two category of C linear categories. Sorry, I botched that. But like you notice that if I were to just want to define one local systems, then I would be looking at functors inside of one cat from G considered as a, or from this G Langlands dual considered as a topological space just into the one category of vector spaces. So here all I've done is I've just replaced one categories by two categories and vector spaces by categories. So sorry, that was kind of a mouthful. And so then one can like try and like think about like what on earth this thing could be. Unfortunately, the torus is like as a topological space is like exceptionally simple. We know that it's the classifying space of its fundamental group. So you can think of this thing as just being B of pi 1 of the of our torus. So this is actually just some lattice. And you can look at functors from that thing into C linear categories. And when you think very hard about like what this thing would be, well, this classifying space, it just has a single point, and then it has basically like one loop for each element of pi 1 like of your torus. And so the unique point should pick out some particular category, let's call it C. And then the rest of the structure is basically just given by these endomorphisms. So this is actually the same as the two category of category C equipped with maps from pi 1 GL into the endomorphisms of C. Okay, so does this make sense?
Well, if you give a meaning to, I mean, do you consider kind of a strict homomorphisms, or it's all infinity?
It's definitely got to be all infinity. Although in this case, it's probably not going to matter because because the torus is so stupid.
Yeah.
So yeah. So for the torus, I think that this literally just is strict. Or sorry, I mean like that you can make everything strict.
Mm-hmm.
So you mentioned that for torus, it's stupid, but what happens if you use the G to be the reductive group? Does the formulation work?
So the formulation won't change as far as what this definition of the sigma model into T star of some random reductive group will be. The issue is that you won't be able to compute it. Like you'll write down this step, and then you'll get stuck. So the formulation doesn't change, but you're I'm not strong enough, or I'm barely strong enough to handle such a thing.
Okay, thank you.
Yeah. Okay, so that's like one guy. All right, and then actually the other side is actually exactly the same. So loc 2 of BT. So again, right, like we're trying to figure out what this will be, and I'm going to literally just use the same definition. But now things are going to be much more complicated when I try and unpack it. So again, oh, sorry, and again, I should have changed my torus to G. Okay. So then, but this, it's bad, but it's actually not that bad, because although this thing is not a classifying space anymore, it's actually like a classifying space of a classifying space. Or sorry, it's a classifying space of something. Something simple. And then this, you can write down is just going to be the two category consisting of categories, but now you're going to have a map from pi1 of G into the endomorphisms of the identity of C. If you work out like what this thing is. And then, okay, so let me say just one sort of a word. The reason that that this thing goes to the endomorphisms of the identity is that this object here has only one object and one morphism. And so the unique object is going to C, and then the unique one morphism is going to the identity of C. And then now you have a whole bunch of two morphisms, and that's like what this, this map is going to be. And then the second thing to notice about this that makes it actually quite complicated is that this is actually an E2 algebra. There are two compositions on the endomorphisms of the identity in a category. There's like a vertical composition and a horizontal composition. And this is also an E2 algebra. Because if you have loops in a group, basically there's both the concatenation product and the group product. And so this map is actually a homomorphism of E2 algebras. It is the requirement that you have here. And so this is actually quite complicated. It's actually very difficult to write down E2 homomorphisms because when you want to resolve, especially like in a homotopical fashion, because when you want to resolve the pi1 of G as a free E2 algebra, like the resolution is like not known, and it's pretty awful. But this is his answer. And actually, let me just do one thing now to both of these examples. So since both of these maps are into linear spaces, like basically I'm looking at linear categories. So this is so this endomorphism is the identity. This is a vector space. Let me actually just go ahead and take chains on this space in order to linearize it. It'll come in handy in a second when I want to compute the dual. Okay, so any questions about these two guys?
Yeah, so in the case of the torus, this is just a lattice. So you're saying was the E2 structure is just trivial, or I mean, sort of the same thing? Or what's going on?
Yeah,
here?
so it's both the addition, but the thing that I'm trying to say is that just the integers, like with like their standard, like commutative E2 structure, if you try and resolve them as like an E2 algebra, you're basically resolving that, like the free E2 algebra is basically built out of like the configuration spaces of points in the plane. And so basically like what you're like doing is like you need to write down some sort of like an interesting, basically like a free resolution of the integers by configurations of points in the plane. And like that like is awful. Yeah, so that's and that's actually gonna like make something that that I'm gonna do in a second actually probably be not kosher. But basically like this is like what Teleman sort of says to do, like in his ICM.
But there are some resolutions for the chains on the E2 operand, even quite small.
Yeah, so maybe you can do this one, but there's like a similar paper. There are like some other papers where I've seen people trying to construct actions like this, and it's like not so easy. Maybe stronger people than me can do it. I'm just saying that there's something subtle. Like if I just put in like a random space here, you like that was simply connected, then you would just get chains on its double loop space here. And then like basically there's no reason for E2 maps to be easy to describe. Okay, so let me now try and move on to the B models. So the B models are basically like very, very easy. Again, I'll start with the sigma model. So for the sigma model, basically he does the following thing. So he says like, okay, well, a coherent sheaf is just a vector space that has an action of functions on it, at least like if you have an affine thing. And the torus, the Langland's dual torus to G is certainly affine. So maybe like one can categorify this definition by just talking about categories that are linear over functions on the torus. So his definition here is just that you should have some notion of a two coherent sheaf, which on an affine space, he just defines to be categories that are linear over functions on this torus. Or actually, sorry, I don't like my notation for that. Let me call it CG. Okay, so you just look at categories that are linear over that. Although there's a better definition which works in more generality, which you can show is exactly the same, which is that this is actually categories that have an action of coherent sheaves on this torus thought of as a tensor category. This is categories with like a tensor action, or module categories for this tensor category. Okay, so that's not so bad. And then this other one is actually literally the same. You just change the Langland's dual torus to G to BG everywhere. So this is the definition I'm going to use. All right, let me just move this around so it's positioned a little better on the page. Whew. Okay. All right. So now, like, we've actually got like all of our players on the board. And when we look at this guy, this guy is really just also the exact same thing as categories together with a map from the characters, a multiplicative map from the characters of G into the endomorphisms of C. Because basically, like, you just need like this category of coherent sheaves on BG, are just the representations of G, and for a torus, like the simple ones are just the characters, and they, not the simple ones. I guess they're just in bijection with characters, and their tensor structure is just given by addition, and there's no like interesting HOMs. So you can write this thing as just a map like this. And then you notice that these two guys are literally the same. So far, so good?
Yeah, at least they are literally the same, as I can see.
Yeah, it's just it's good. And then it turns out that these guys are also literally the same, because this thing is just functions on the dual. Okay, so we've done it. We've proved mirror symmetry, or Teleman has proved mirror symmetry in the simple 3D mirror symmetry in the simplest case. And so basically, like, this is going to play the role in 3D mirror symmetry that like the equivalence between like coherent sheaves on a torus and local systems on the dual torus plays in ordinary mirror symmetry. This is kind of like the key example that kind of gets everything off the ground. I should say that Teleman like tells you what to do for the, actually, like, I think this result was actually known to Kapustin. And I think Teleman's contribution is actually figuring out how to generalize it to non-abelian groups. But let me like just say like one sort of a subtlety that basically like has really bothered people. But I'm going to claim that it's actually going to be a feature and not a bug. So one thing that like really bothers people is like if you try and write this thing in sort of like a micro local sort of way. So what I mean by that is like write it as things about the cotangent bundle as opposed to writing it as things about the base. Then like one can sort of rewrite this like in the following way. So you can say that there's supposed to be some sort of like a 2 Fukaya category. I think I've been using A3D to refer to this thing now, of T star BG. And I'm just now rewriting things that I wrote on the other page. So our definition of that was that it was 2 co of BG, or sorry, not 2 co, 2 local systems of BG. And one can also write down the B model. But both of these things, there's some sort of like a annoying fact that like if you think about like your Fukaya language, a local systems is not just the Fukaya category of a cotangent bundle. There's actually many Fukaya categories of a cotangent bundle, depending on like the data of what's called a Lagrangian skeleton. And this is actually only the Fukaya category if you give it the 0 section as your Lagrangian section, or as your Lagrangian skeleton, and similarly here, and similarly for the other. So basically, there's a Lagrangian skeleton actually hidden in the game that like isn't present in Teleman's ICM. And I sort of claim that this thing is going to be a feature. I've just rewritten, like I've just literally rewritten what I wrote on the other page, just in like a more micro local sort of way. So here, what I'm claiming is that these categories, A3D, that they should depend on like both a hyper-Kähler manifold and some sort of like a Lagrangian skeleton. And so this is basically supposed to be a generalization of the fact that now we know that the Fukaya category, actually, sorry, let me say that this is a cotangent bundle, that we know that actually that the Fukaya category of X actually also depends on the choice of Lagrangian skeleton. And similarly, there's like some sort of behavior like this, like on the B side.
And
So
this X is a hyper-Kähler or like holomorphic symplectic?
Let me just say holomorphic symplectic for now.
Yeah. All right. Some C-star action on it or what?
Eventually, there will be all of these things, but actually, like this thing does not have like a conical. I guess it does have an action. Yeah, so I guess like what I'll want is that for this thing to be a holomorphic symplectic.
When you say Lagrangian, do you mean that it's Lagrangian in the C infinity sense, so it will be holomorphic as well?
Holomorphic Lagrangian. And so this thing is like holomorphic symplectic.
So this version of Fukaya is like a partially wrapped kind of thing, or
Yeah, exactly. This is so basically what I'm saying is that this example, it's not just about like any just like in the theory of the ordinary Fukaya category. If you just give me like a non-compact symplectic manifold, that doesn't specify what the Fukaya category is. You need to like specify a skeleton to make that well defined. Like in the non-compact case.
but the algebra, the version you're thinking is more along like a constructible, some kind of stratification with for constructible sheaves or some kind of microlocal thing, or
some sort of micro. This is supposed to be the like the cotangent.
Okay.
Cotangent. Sorry, the conormal bundles to like strata. So
Right.
so microlocal.
right?
Yeah, but so your X, do you assume that it's exact?
Yes, for now. I don't know what to do when it's not exact. And like technically, like I think that once you've asked for this U1 action, I think that forces it to be exact. It's like being Louisville.
All right, so maybe
right.
not,
So if this thing scales, sorry. So right now I'm not trying to. I was not at this point planning to try and tell you the general, like the most general sort of thing that could go in here, but I was just trying to tell you like one simple example. But then let me just try and say like one other reason why I want to think of this thing like a wrapped Fukaya category. Is I wanted, so back when I had told you guys about like the physics construction, I had mentioned that that in the A model, that there was this really great result of Doan and Reshikov, where basically they computed in a cotangent bundle what the HOMs between the graphs of one forms look like. And I had sort of claimed that like this was actually not enough, like on the A side, and the reason is that if you think in an analogy with like the with just the ordinary Fukaya category of a cotangent bundle, like the wrapped Fukaya category is not generated by the graphs of one forms, it's generated by a cotangent fiber. And like what I want to claim is that like this thing also is going to behave like a wrapped Fukaya category. It's going to be generated by a cotangent fiber. So let me try and like argue for why that's true. The reason like why I expect that to be true is that it's known for like other reasons that under mirror symmetry, the Lagrangian BG sitting inside of T star BG gets swapped with this cotangent fiber. So that's actually something that's that you can compute in other ways. like even without constructing this category. There's like other computations that you can do that tells you that this has to be the case. And then we know, like from the model that we wrote down before, that the endomorphisms of this BG, like if you kind of think through what the dictionary is going to be, like this thing is actually going to end up just being the coherent sheaves on BG as a tensor category. And so now I want this thing to be the same, and I need this thing to be the same size. And so the only way that this thing is going to be the same size is if this thing is basically some category of sheaves on the loop space of G of L under convolution, or sorry, under loop concatenation. And this thing, if you think this thing directly categorifies the description due to like maybe Abadandalo was maybe the first people to do it, but also Abazayed of the endomorphisms of T star 1 inside of the cotangent bundle. So the picture that you should have in mind is that this thing is some sort of like a wrapped Fukaya category. You have your cotangent fiber, and then you have some sort of wrapped version of it. And there's like a integers version of these, and these things are in bijection with the representations. So like what this thing tells you, let me just state this in a much more sort of clean way, is that there should be some sort of like a version of this category which is basically generated by the conormals, the subvarieties. And inside of that thing, you expect something like the endomorphism, or sorry, the HOMs between two conormals. So if I have the conormal to some subvariety, just call it X inside of B, and some other subvariety, let's call it Y inside of B, like you kind of expect this thing to be something like sheaves on the space of paths in B that start at X and end at Y. And this is basically a direct categorification of like the string topology construction of the wrap Fukaya category. So there's like basically a well-known like sort of topological construction of the wrap Fukaya category where you would just take chains like on these path spaces. And I'm saying that this, at least for this 3DA model, when you have a cotangent bundle and like a strict base, like you ought to just categorify that by promoting chains to sheaves. Okay, so this was all very fuzzy. It was just trying to like give you like an idea of the sort of thing that you can expect to happen. Let me like try and actually be like a lot more precise. So maybe like let me pause. And how much more time do I have? I guess probably 10 minutes.
Well, just, I mean, you can speak for as long as you can. The seminar is informal in terms of time as well, but so you can speak for another half an hour if you want. Okay,
yeah, then basically like just stop me when you get bored.
Those who are bored, they can just leave.
Just leave. Yeah,
yeah.
That's right. All right, so let me try and say something that's like a little bit more precise. This actually comes from like a physical thing that we know. So one thing that we know physically is that there's expected to be a relationship between these three categories, or sorry, these two categories. And something that's called category O. So let me sort of just tell you what the physics is, and then we'll actually just go through one example of like where this thing comes from. So roughly like what the physical construction is that one can look at these 2D 2,2 boundary conditions for these 3D n equals 4 theories. And then one can look at like a dimensional reduction of this 3D theory to a 2D hyper-Kähler sigma model. And like the way that this thing sort of works out is that the A twist, so again, like I had to choose a, in order to make these things, when I chose this 2,2 sigma model, this thing chose complex structures on what are called the Higgs and Coulomb branches of the theory. Won't try and tell you what those things are. But anyway, so I have some complex structures. And physically, it's known that the A twist goes into the A twist on the Higgs branch in complex structure J, if these complex structures are both I. And this B model, or this B twist, goes to the B model on MH in complex structure I. And that there's like this interesting interpolation that one happens when you have A models and B models on a hyper-Kähler manifold, which basically is deforming by a Poisson bivector. In the B twist, or if you're in the A twist, it's the same thing as turning on a B field. So your bivector is basically coming from the inverse of omega j plus I omega k. And so there's basically, it turns out that there's like some reduction that is actually the same, that's like actually intermediate between the A model on the Higgs branch and the B model on the Higgs branch. And what we sort of worked out is that this is actually category O. So like if you take this A3D and B3D and you reduce them to this like intermediate point, this thing is like a periodic version, a Z2 periodic version of what's called category O.
And so category O for what?
For the Higgs branch. For the Higgs branch.
Which means that what? You quantize the algebra functions on the Higgs branch. And
yeah, so let me write this thing down. So this thing is another name for you look at deformation quantization modules on the Higgs branch, and then there's some particular Lagrangian skeleton.
So why it's only Z2 if your
so let me tell you what the
let me
tell you what the decategorification functor is. So this decategorification that leaves you in this intermediate point, it's called decategorification in omega background. And basically what this is you take your 2 category and turn it into a 1 category by doing periodic cyclic homology to the Hom spaces. And since periodic cyclic homology is Z2 graded, then this thing is Z2 graded. Okay, so that's like something like very general, but let's just do like an actual example where we can see what's going on. All right, so let's try and think about abelian gauge theories. So these abelian gauge theories are places where you can actually do all the computation. I'm going to want to tell you what the mirror is, so I'm going to describe these in an overly complicated way. So let's assume that I have an exact sequence of tori. So I have C star to the n, and then I have a torus sitting inside, and then another torus as a quotient. This torus C star to the n just naturally acts on T star C to the n, which is holomorphic symplectic or even hyper-Kähler. And so this thing is called the matter representation. This group here is called the gauge group, and this leftover residual symmetry is called the flavor symmetry. And one thing that will be important about it is you could look at the stack T star C to the n mod G, and it will have a residual F symmetry. There are some parameters like in this theory. So these are going to let us get away from stacks and just go to like ordinary manifolds. So the first one is called the Fi parameter, but it's just a GIT parameter. And so this is just a character of our group G. And just by well-known GIT stuff, this thing determines some open subset inside of this cotangent stack, which is our GIT quotient. And this is what's called a hypertoric variety. So these hypertoric varieties are extremely nice. They're going to be like the analog of toric varieties for 3D mirror symmetry. And then the extra parameter, the other parameter is called a mass parameter. And this thing is a C star sitting inside of F. And because F acted on this quotient, or sorry, on this T star of C to the n mod G, and also this MT, then C star also acts on both of those varieties. And then from this thing, I can basically get a Lagrangian skeleton. So if I assume that my if I assume that this C star has like isolated fixed points or dimension 0 fixed points, then the attracting sets will actually be Lagrangian. And so you can get a Lagrangian skeleton, which is basically consists of like the attracting sets for this C star inside of this stack. If you are uncomfortable with doing attracting sets on a stack, which I am a little bit, one can just also do the attracting sets on the GIT quotient, and that'll be good enough for most circumstances. And then one could ask, like, what is the 3D mirror to this theory? And so the nice thing about these abelian gauge theories is that they're self-mirror. And so the mirror is basically you take the Langland's dual sequence. So that basically now you have the Langland's dual of F, including into C star to the n, and then mapping down to Langland's dual of G. And so I'm going to call this Langland's dual of F G shriek and the Langland's dual of G F shriek. And these basically define, this exact sequence basically defines the mirror theory. And the action on the parameters is just that they get swapped. And then there might actually be a sign on one of these, but I always forget. And so I'm just going to be sloppy. But the important thing is that these abelian theories, they're closed under mirror symmetry. So that means that you can study them without leaving this class. And so basically they're the best testing ground for all this sort of stuff. And so then the conjecture, which is this two categorical abelian 3D mirror symmetry conjecture, although I should say that it's basically a theorem by now, is that if you look at the 3D A model of the hypertoric variety that you get by looking at your abelian gauge theory with this parameter T and Lagrangian skeleton corresponding to M, and that's going to be equal to the B-type category where you look at the mirror theory with the same sort of thing. And the interesting thing about this, I said that this should be related to category O in some way. And the specific way in which that it's going to be related to category O is that if you take periodic cyclic homology of the Hom spaces, the Hom categories, then now you'll just have Hom vector spaces, and they'll be, modules over the equivariant cohomology of the S1 equivariant cohomology of a point. So this is our C beta inverse, basically the equivariant cohomology of a point with the parameter inverted. So anyway, so you can take this periodic cyclic homology, and it'll and what you're going to get is just a 2-periodic version of category O. And the specific way in which you're going to get category O is we sort of said that these A models, that they're going to be generated by things that look like cotangent fibers if you, in the case of a cotangent bundle, this thing's going to be generated by cotangent fibers. And if you have a more interesting skeleton, it's going to be generated by like transverse Lagrangians to each component of the skeleton. And that like corresponds to the projective in O, if you know about that, which you probably don't. But and these this B model, it turns out it'll actually be generated by the components of the skeleton. And those correspond to the simples in O. And so this thing is actually going to be categorifying a specific isomorphism between category O for M and for M shriek. And it's the one where you identify endomorphisms of a projective with the Axt algebra of the mirror of the simple on the mirror. And you might worry that like this thing is all concentrated in degree 0, and this thing is actually could be an interesting cohomological degrees. That all gets saved for you by the periodicity. Whew, okay, so sorry. So that's the statement. And so the thing that I have to do in order to make this, to tell you like how this thing becomes true, is I need to define all of these categories for you.
So, but this sort of a categorification of the Koszul duality for the level of HP, yeah? Because your this duality between projectives and simples, it's sort of a Koszul duality.
Yeah, exactly. This is the Koszul duality, and this is it's going to categorify that.
Yeah.
And the geometric input that's going to be responsible for this is kind of like in this very simple example, I swapped the 0 section of my cotangent bundle with a cotangent fiber. And so this thing is going to be like my simples. These are like components of my skeleton, and these things are transverse to my skeleton.
Okay.
And so that's like roughly like what we expect this thing to look like. And then let me tell you something that's like unfortunate. So something that's unfortunate is that like I was really hoping that this category would only depend on the hypertoric variety MT. But it seems as though that this A-type category, if I want this mirror symmetry to hold, it actually can see the quotient presentation. And the way that you can see this is that like the very simplest one of the very simplest examples of 3D mirror symmetry is the theory for T star C to the N is mirror to the theory where you have your gauge group being C star to the N acting on T star C to the N. And whenever you put on an FI parameter for this thing, whenever you choose a stability parameter, this thing is just always a point. But like this thing can actually has like a very interesting skeleton. It's actually C to the N. And so if you use our ansatz, that basically the B-type category for T star C to the N with skeleton C to the N should just be modules over coherent sheet. This thing should just be CO2 of C to the N. This can clearly see N. So this guy can very clearly see like what n is, and this point cannot see what n is. So there is no way that this conjecture could hold if this category here only depended on the hypertoric variety and not on its specific embedding into a stack. This sort of thing is actually already very familiar because lots of people have studied things about 3D mirror symmetry. It's well known that when you're computing things on like a curve, that you actually see quasi-maps appearing, Kunkov studies like quasi-map invariants of these hypertoric varieties and quiver varieties and other things. And quasi-maps depend on an embedding of your variety into a stack. And so there's something about this like compactification that's visible. Anyway, this is like a flaw of, in some ways it's a flaw of the theory, but in some ways it's it just has to be. Anyway, so I just wanted to say that. So let me tell you just the easiest example of a mirror pair. So the easiest example of a mirror pair is when you have a three-dimensional torus to start, and your gauge group, you choose the diagonal inside of C star to the 3. And this thing just ends up being, when you form like your hypertoric variety, if you choose your GIT parameter, this thing ends up just being T star P2. And there's these really great pictures that you can draw of hypertoric varieties, which helped you study these theories. And basically there's this, you can take the arrangement for the toric variety P2, and you can just extend all of your hyperplanes. And if you do that, it's actually like very interesting that the components of this new arrangement, like this is a bunch of toric varieties that are all glued together along lower dimensional toric varieties. And what these things actually are is this is actually the 0 section of T star P2. This is P2. This is actually the conormal to a P1 inside of P2. And this one is actually like the cotangent fiber to a point, or the conormal to a point. And so that's a copy of C2. And so actually this picture actually shows you this the simple holomorphic Lagrangians inside of T star P2. And even more so, you can choose like your mass parameter, and that picks out some direction in this plane. And this mass, and if you want to know like which components are in my Lagrangian skeleton, all you do is you just look at all the chambers that are actually bounded. Like you think of this thing as being dot product with this vector as being a function, and you just take all of the components that are bounded above for that function. So these three guys, that function would be bounded above, but like this guy, like that can clearly get infinite, like as you go out here. This one can clearly get infinite as you go out here, and so on and so on. So this actually lets you see both your MT and your skeleton in very easy terms. And then the mirror to this guy, it's interesting that these things are not of the same dimension. So this is very different than 2D mirror symmetry. And so the interesting fact here is that this thing is actually the resolution, the Krapent resolution of C2 mod the cyclic group of order 3. So this guy, so the mirror, it has a skeleton which looks like two P1s glued together, which are the normal things that you would see in this Krapent resolution. They're the fibers over the singular point. And then basically there's just some extra C fiber, which is just sticking off. So that's the form of this Lagrangian. Okay, so this is the simplest example of a mirror pair. This hyperplane combinatorics is basically going to be the thing that's going to let us solve this problem. All right. So let me, yes, so these, I guess this slide's a little bit old, so I guess we've actually done this now, but okay, so I need to give you an ansatz for what this category A3D is going to be. So I told you it's some properties that it should have, or like some ways that it should behave, but I haven't given you a definition. And my ansatz is that I'm actually going to first look at a skeleton, which is not an example of a lambda m. But for this particular example of T star C with the coordinate cross as the skeleton, we actually know what the answer should be. And that's due to Kapustin-Vyas-Setter and Teleman. We know that it should be something which is called like a perverse Schober. And so a perverse Schober is supposed to be a categorification of perverse sheaves. So these perverse sheaves on C with a singularity at the origin, these things are also like a equal to like the micro sheaves of T star C with skeleton given by the cross. And it's well known that these have the following description. They're just given by two vector spaces, which are the nearby and vanishing cycles of your sheaf. And you should have a pair of maps going from between the nearby and the vanishing cycles, or I guess the vanishing and the nearby cycles. These maps, L and R, should satisfy the following property: 1 minus R times L and 1 minus L times R should be invertible. So the way in which like one actually like proves that this description, or like understands this description, is that inside this category of microsheaves, or inside of your Hyper-Kähler category, you have your Lagrangian skeleton, which has two components. And then there are linking disks basically to these two different components. And your functors of nearby and vanishing cycles are basically supposed to be like intersect with this linking disk, or take the microlocal stock away. So this is basically kind of like a, again, a version of this thing where I was telling you that when you had a cotangent bundle, which had just a single component in its skeleton, that you should use the cotangent fiber as your measurement in order to describe the category. And this is also the same in like a wrap Hyper-Kähler category. Okay, and then so one just wants to categorify this description, and Kapustin-Vyas and Teleman already did it for me, so I don't have to be clever. So what they say is that you should upgrade each of these vector spaces to categories. So you should have a vanishing category and a nearby category. And then these maps, you should upgrade them to functors, going back and forth, L and R. They shouldn't just be any functors. They should be adjoint functors. And once they're adjoint functors, well, then there are natural maps from the identity on CFI to the composition RL, like just the unit of the adjunction. And there's also the co-unit of the adjunction, which is a map from LR into the identity of the nearby category. And basically, you just take the cones on these morphisms, and those are the analog of these things that were supposed to be invertible below. In fact, I'll just use the same notation. So one of these is T phi, this other one is T psi. So this equation of just taking the cone it basically exactly categorifies this 1 minus RL or 1 minus LR. And then I just don't, the one thing that's slightly complicated is that for certain reasons, you don't just want to take the cone, you want to shift it in some degree. But basically this is just taking the cone. And then here you asked that those things were invertible, and I'm just going to do the same. So like here I asked that T phi and T psi were invertible, and here I'm just going to ask for T phi and T psi to be invertible. Okay, so that's going to be my ansatz in this particular case. And then I just want to get everything else out of this one case. If I can just understand this case, then like I'm really good. Okay, so let me like describe now like what the B side is for the same, for roughly the same thing. The B side in this story is actually way better understood and is much easier. So let me suppose that I want to understand like what is the 3D B model for some cotangent bundle where I have a skeleton which is just given by a union of conormals. Well, so I can take a map, can make a map from X to Y, where X is the disjoint union of the bases of all of my conormals. And I can take the fiber product of X with itself over Y. And it turns out that that will have that the category of coherent sheaves on that fiber product will have a monoidal structure under convolution. And I can just look at categories with an action of this monoidal category. This thing is like relatively easy to understand. So let me, before telling you about this Koszul duality, let's just look at an example. So the mirror to T star C with the coordinate cross stratification is going to be T star C mod C star, with the stratification also given by a cross mod C star. And so if one uses this proposal of Arinkin, then basically one takes the disjoint union. So these are the conormals to C mod C star, that's the 0 section, and 0 mod C star, that gives me this cotangent fiber, respectively. So take the disjoint union of these two spaces. And then now I take their fiber product over C mod C star. And then I'm going to look at like modules over that tensor category, or over that category with the convolution monoidal structure. And there's going to be 4 components in this fiber product. Basically, I can intersect the 0 section with itself, and I just get the 0 over the whole space. So that just gives me the whole space. I can intersect the whole space with 0 mod C star, and that just gives me 0 mod C star, or I could do that the other way and I'll get 0 mod C star again. And there's one example where that's interesting, where when you intersect 0 with itself inside of C, when I write this intersection, I always mean it in the derived sense. And so you're actually going to pick up some interesting derived structure here, coming from basically the Tor of C with itself over C adjoint X. And this thing can be Koszul dualized into like a nice form where you can think of the category of coherent sheaves on this odd derived guy as just being the category of perfect complexes on an even guy, but with a funky degree shift. So that will come in handy. And you can think of this copy of C dual, you can actually think of that copy of C dual as being this cotangent fiber. Sorry, I should have a mod C star there. And this, yeah, this guy is this cotangent fiber. Okay, so first before saying anything more general, let me just stop and ask about whether people are with me.
At least some of them, yes.
Okay. Yeah, basically, like it's just so hard with no faces to know.
Yeah, it's a disadvantage of Zoom, but anyway, some people can show their faces on the screen, yeah, if they like to do that. Yeah, you can go ahead, yeah.
Yeah, okay. So anyway, so this thing is like some interesting 4-term, it's just like a matrix, it's just a categorical version of like a matrix. Right, like it's just like a 4-term, it's like just a matrix category. And there's just a generalization of this result where I managed to identify this self-intersection of 0 with itself over C with functions on like this cotangent fiber, or sorry, with sheaves on this cotangent fiber. And that basically is this Koszul duality here, where if you do the self-intersection of X with it, if this is a smooth embedding or whatever, you do the self-intersection of xi with itself over y, and you look at that as like a convolution, as a thing over convolution, then that's Koszul dual to just perfect complexes on the conormal with a funky degree shift and then just with the ordinary tensor product. And this ambiguity in like this two-shifted thing, this comes from the fact that like in physics, the Rozansky-Witten theory is not really supposed to be Z graded, and I'm making it's only supposed to be Z2 graded, and I'm making it Z graded in some funky way. And like it causes just all sorts of strange degree shifts to show up. Whew, okay. So then now actually like the key result out of like all of this, the thing that makes like everything sort of go is a theorem of myself, Ben Gammage, and Aaron Mazel-Gee. And so the first thing is going to be just completely out of the blue. So the first part of this theorem is that there's an equivalence of three categories between actually in my old notation, or in the notation that I was using, maybe I could call this thing loc 3 of BT. And then there's also a loc 3 of BT check, or BT Langland's dual, or sorry, a co3. And these things are the same. So this is just some version of the kind of computations that I did earlier in this Teleman example. This is actually an example. This is actually the like three categorical version of Langland's for a torus. But anyway, one can prove this result. It looks extremely fancy, but it's no more complicated than saying that the fundamental group of C star is Z, and also the number of characters of C star is also Z. Like it's some fancy looking thing, but it's actually like there's nothing in it. But so that's the first thing. So then the second thing is that one can study this category of perverse, this 3D A model of T star C with this coordinate cross stratification. And we've said that that thing is perverse Schober's. And we know that like this stratification is actually invariant under like the S1 that rotates C. And one can actually lift the action on sheaves to an action on Schober's. So like this category of Schober's actually has, this two category of Schober's actually has an S1 action on it. And that S1 action makes it into an element of this, three category loc 3 BC star. So that's the first part of this equivalence. That's the first statement, is that this thing has an S1 action and you can lift it into this category. The second thing is that this B-type category, which we described in this Arinkin way, for T star C mod C star with the coordinate cross skeleton mod C star, this thing has a natural, this two category has a natural action of coherent sheaves on BC star with its tensor product. And that actually puts it inside of coherent sheaves, or three coherent sheaves on BC star as well. And these are actually dual. This C star is actually dual to this S1. And so the first statement is that one can actually like upgrade each of these objects to categories with an action. Then this equivalence like basically doesn't basically like preserves underlying objects, and under this equivalence, like this object literally is this object, or just becomes this object. So that's like the first statement. So the upshot of all of this is that like now I don't just know what perverse sheaves are, I know what equivariant. Now I don't just know what perverse Schober's are, I know what equivariant perverse Schober's are. And because the hypertoric varieties that I was going to build were just quotients of vector spaces by torus actions, the categories that I want to build are actually going to just be certain categories of equivariant Schoebers. Okay, whew. And then the last part of this theorem, which is the part that is still being written up, is that we've worked out how to change the skeleta. Like I know like how to basically like add components and subtract components to the skeleton. And similarly, I know how to pass to open subsets in order to do GIT quotients. And the theorem that we can show is that removing a component from the skeleton is dual to deleting a component from the dual component from the entire space. So I'll explain this in an example in a minute. But once you put all of these three things together, then you're basically done. You've proved 3D mirror symmetry for all of these tori. So let me just tell you something that this 1 + 2 implies. So this 1 + 2 implies that that I know what it is to have an S1 action on perverse Schoebers, and in particular, like one can just gauge that action, or you can take invariance for it. And that's going to be my definition of what it is to have the 3DA model of T star C mod C star with the same skeleton. So this is the mirror situation to what I was looking at before. And similarly, by this functoriality under like the Langlands equivalence, you can actually see that taking invariance or that quotienting corresponds to like unquotienting. So what ends up happening is that on this side, you can take your Arinkin category and remove all the C star actions. And that will be what we had already defined to be the 3D B model for T star C star with the same skeleton. This looks like the exact same matrix, except you just get rid of everywhere I'd modded out by C star before. And like by this, these two facts together, you actually get that these are the same. So this is like a consequence of this compatibility with the abelian Langlands correspondence. So this is like very handy. And you can use this same sort of thing basically to like understand what it is to have perverse Schoebers on, you can take, C with its stratification by the origin and take the product of that space with itself a bunch of times. So you get C to the n with a stratification by like maximal torus orbits. And you can look at like any like subtorus of C star to the n and take the fixed things. And you find that actually you find the Arinkin, the mirror Arinkin category. So this thing like actually gives you sort of 3D mirror symmetry for any, but with the wrong skeleta. So like from just this 1 and 2, like I can handle everything involving the groups. And then this 3 is basically going to be what I'm going to do to change the skeleta to be what I want. Because the problem is that here I have some terrible stacks. And here I have a skeleton that has too many components. And what I want to do is pass to the GIT quotient here and remove components to the skeleton here. And what I'm telling you is that like those two, you can prove that those two operations are exchanged. And that gives you everything. Oh, okay, so maybe let me pause. So the so I can do like one of two things. So I could either tell you how one proves this equivalence, number 2, or I can tell you, or I can show you examples of stop removal and deletion. And so do people have any, I mean, I can certainly do both, but I can do them in either order. So do people have a preference of which one they'd rather see?
Well, for me, it's up to you, because you know better the kind of the logic of your talk. So I mean,
they're basically just completely independent. So basically, like this one would tell you more about like what the categories look like for more complicated examples. This one possibly, and maybe would explain what this theorem even means. But Yeah, let me do 3 first, and I'll come back and do 2, since that's like totally independent of everything else.
Okay.
All right. So let me just show you an example of this stop removal / deletion. So the problem that I had is that this skeleton never actually shows up in 3D mirror symmetry because it's not the attracting set of any torus action. But there are 2 possible torus actions on T star C star, and one of them has its skeleton being the 0 section, and the other one has it being the cotangent fiber. So what one wants to have is like an operation of like stop removal, which lets me simplify my category by like removing a component from the skeleton that goes to either of these guys. And similarly, like this thing is also not showing up in my mirrors, shouldn't show up in my mirror symmetry statement because this is a stack. This isn't actually a like a variety. And so what one needs to do here is I have to remove components of this space in order to do the GIT quotient. I have to remove the unstable points. And so again, there are two characters of C star that I could choose, or well, 2 signs, either like I could choose the positive one or the negative one. And in either case, my GIT quotient in the end ends up being just the point, but it actually ends up being a point in different ways. So if in one setting, if I choose one of my characters, I end up removing the 0 section. And then I end up getting the cotangent fiber, or I end up getting, so I end up taking like the space looks like a cross mod C star. And then I end up removing the 0 section from it in order to do my GIT quotient. And I end up with something that looks like this. And then this is a 0-dimensional space, or that's just isomorphic to the point. It's just C star mod C star. And then it has its skeleton just being the point because there's no interesting skeleton there. So that's like one example. And both of these 2 categories are just completely trivial. So these were interesting 2 categories, and these are just DG-cat. And but there's 2 different ways of getting to DG-cat, depending on whether I remove this component of the skeleton or whether I remove the 0 section or the cotangent fiber. So I'm getting the point in 2 different ways. And so one can like do this in like a slightly more complicated context. So you can do the same thing where I swap A and B. Or sorry, where I swap whether I'm doing the restriction or deletion on the A side or the B side. And this one is actually like extremely interesting. So here I can take T star C and I can, T star C mod C star, and I can just remove a component from the skeleton. So in this case, this was this thing we were calling, here I just have a cotangent bundle with its 0 section. So that's something that we already knew. It was just that thing we were calling 2co before. And on this side, you're going to get also, oh, sorry, there shouldn't be a cotangent there. And this one, you're also going to get the same thing, except for this one is going to be co2, but you're going to have a weird degree shift. And the incredible thing is that like if you do this deletion operation, it actually works out the same on the other side. And what this ends up being is it just ends up being that you forget one of your 2 categories. So this thing had like a nearby category and a vanishing category. And here you just either remember the nearby or the vanishing, and then you continue to remember like your twist together with its map. And this thing is corresponding to O C mod C star with grading shift by -1 maps by X to O mod C star. It's like what this thing is dual to. So at least this gives you some example of like what this deletion contraction looks like. And this is one of the examples I had mentioned earlier, where this shows that in fact that things are like a little bit interesting, because like these categories here, they actually they're not actually equal to loc 2 of C star, which is what you might have imagined if you just take T star C and remove C from it, or remove C dual from it actually is better. Like you might imagine that this thing is just T star C star, but somehow there's some additional structure on this 2 category, which makes it different than loc 2 of C star, but they both decategorify to the same thing. So there's some like extra like weird structure like coming from the fact that this copy of T star C star is living inside of T star C. That's like visible at this 2 categorical level. That's not visible when you decategorify your sheaves. So there's something like really funky going on here. Okay, so that's a mystery. Here's just a way more complicated example where I show you how to build coherent sheaves on P1 using the A side, but I think that that's too complicated. So let me just tell you about the key technical result that makes this whole thing go. So the question is like, how do you prove this equivalence between perverse Schober's on C with a singularity at the origin, and then this weird Orinkin category. And the key result is actually uses something that's just like really wild called like Smith ideals. So like one can ask the question that like, suppose that I have a just an adjunction between 2 categories. So one has a monad, which is just R times L. And that like comes with this structure of basically a unit map and then a multiplication map. And that gives you some algebra inside of the endomorphisms of C. And like one can ask, like it's possible to form the fiber of this map from 1 to M. So you can think of that as being like the kernel. You can take the kernel of this map from 1 to M. And you can ask, is there some structure on this kernel that actually completely knows the multiplication on M? And like the wild thing is that there is. And like this thing is called like the structure of like a Smith ideal. They were discovered by Jeff Smith. And it's like basically what you can do is you can write down like a tensor functor from the integers, the non-positive integers with the tensor structure given by just addition. And then this category has a morphism in it whenever one integer is smaller, you always have a morphism from like a smaller integer to a larger integer. And so like this thing is some interesting tensor category. And you can actually like, and it turns out to give a tensor functor here is like you really just need to know where this one map from -1 to 0 goes. And so that thing goes to this kernel, this fiber of eta, and then 0, since is the tensor unit, has to go to the identity. And so you can like write down like, but the fact that this is a tensor map puts a bunch of interesting homotopical structure on the fiber of eta. And it turns out that basically like this structure on the fiber of eta completely lets you recover M. So if you take the co-kernel of this map, that you can go back and get M as long as C is a stable category, or endomorphisms of C is a stable category, you can go back and forth. And these things are just exactly the same. So sorry, in order to have this be true, I need C to be end of C to be stable. So you need that in order to know that the fiber of a cofiber and the cofiber of a fiber or null ops. So that's like pretty crazy. So this actually like answers, I think, like or maybe like tells you something that people had like wanted to know before, which is like how much information does the twist know in a spherical functor? And the answer is that like if you remember the fact that the twist has the structure of a Smith ideal, then like it exactly recovers the monad, like in your spherical functor. So I think that this is something that like is like I think is like a question that people had sort of had. And then moreover, if you ask, so yeah, so like if you're actually in the spherical setting, so where you ask for your twist, which is the fiber of eta, I don't know why I decided to call it I there. Is invertible, then you can extend this whole, you can extend your tensor map from the non-positive integers to just all integers ordered under, thought of as a partial order. But then as long as this end of C is stable, then you can linearize this category. And it turns out that the stabilization of just the integers, like thought of as a partially ordered set, if you think of that as a category, and then just make it C linear in the easiest way, that's actually coherent sheaves on C mod C star. So the fact here, right, is just that you've got a bunch of different twists of the structure sheaf just by different weights. And depending on how you set up like your positive or negative weights, then you'll get a map in one of these two directions, which is just multiplication by the coordinate on C adjoint X. So this is right. This is just think of functions on C as a graded object. And this is like a degree 1. X is a degree 1 map. The function on X is degree 1 map. And basically, like this is all the structure in that category, is that basically you just have an integer's worth of objects and one map between each one. Sorry, and then if you stabilize that, like that gives you everything.
Hey, Justin, sorry, can I interrupt you with a question? So
Yeah.
if you have a monad, which is an algebra in endomorphism of C, then is that functor from Z less or equal than 0 to endomorphism of C, is that just the bar resolution of this algebra? Because it kind of looks like it could be.
Is that the same as the Adams resolution?
No, I mean bar resolution. So you map your integer like negative k. So negative. Well, wait, negative 1 goes to 0.
No, negative 1 goes to the fiber of eta.
Yeah. Oh. I see. Well, yeah. This is not what I'm gonna.
So if you look at our paper, like we give a formula for this functor. I think it's like they call it like the Adams tower or something.
Okay.
But anyway, so the point is that like so this is where everything comes from, because this is one of the entries like in the matrix, like the Arinka matrix category. So like if you look at this guy, like a tensor functor from that is exactly this entry in my matrix category. And if you work out the second entry, this guy corresponds to the comonad. And then these other two guys, remember, just the left and the left adjoint and the right adjoint. Like that's all the data that's in them. So like this, so like if you work out like what this thing is it's just actually you just took the category, the free category containing an adjoint, and if you just stabilize it, you'll see that it's exactly that matrix I wrote down. But that was like something that like wasn't like sorry, it's that matrix I wrote down after you invert the twist. Which is something that I think that like was totally like unknown, or like what. And it's actually very interesting. These Smith ideals, like basically topologists invented them because they wanted to know what an ideal was in a ring spectrum. And then basically they just gave up because they was like, man, these Smith ideals suck because they tell you that every single algebra is the quotient of an ideal in the trivial ring. Like the trivial ring being 1 in this case, And so they're like, this theory of ideals is not going to be good for constructing like a spectrum, or sorry, like a spec of a ring spectrum. So they just decided that this notion of ideal was useless and then threw it out. But then we found like a use for it like later on. Okay, so that's, I think, way more than enough. And I just wanted to thank you guys for sticking around and listening to me ramble. And yeah, I hope that it was at least somewhat interesting.
All right. Let's see. All right. So thank you very much. Now it's time for questions. So actually, Irina started this question session. Okay, but are there other questions or maybe comments? So do you understand that it's all about this torus, I mean, sort of a torus case, like categorification in the sense of Teleman's story?
Yeah, so the, I'm sorry, yeah.
Yeah, I mean, if the group is if the gauge group is non-commutative, so it's...
So if the gauge group is non-commutative, the B side, there's no problem. So basically, if you wanted to do something like study the Rozansky-Witten theory of a quiver variety, which is the key interesting example with there's a skeleton for category O for a quiver variety that people know about. You can study that using this Rankin definition with basically no problem. So the B side is clear whether things are abelian or not. The A side is completely opaque if you're non-abelian, and basically the problem is here. So the problem is in the way that we proved our result. So the way that we proved our result is that we did this a primitive equivalence, where we just proved the case of T star C versus T star C mod C star. And then in order to get everything else, we worked out what the equivariant version of the story. So we said, okay, perverse sheaves on C with a singularity at the origin, there's an S1 action on that category, we can lift it. And then we worked out what the lift was on the B side. And then basically we proved some kind of way in which these things were exchanged. And we proved this result that ticking invariance on one side undid ticking invariance on the other side. Or basically that's a consequence of this compatibility of these, the fact that these objects can get upgraded to objects here, and that there's this functoriality. But the problem is that this strategy can't work in the abelian case because I cannot make sense of these guys in the non-abelian case. I don't know what it is to have a 3 category with an action of a non-abelian group.
Yeah, even for the Fukaya category in the presence of some action of the reductive group, it's I'm not sure that it's had been worked out in the big generality.
Yeah.
Without categorification, because log 3, after all, it's if you go two degrees down, it will be just lock on something local system, as you mentioned. It's just a Fukaya of the cotangent bundle in some properly defined sense. But if if it's not a local, if you do not have this thorough section, and if it's something more complicated, I don't know. Actually, I have maybe another question again about generalization. You mentioned that actually your examples are either cotangent bundles to something or cotangent stacks, which means probably that these are targets for your sigma models. Am I right?
So these are, so in this case, I started out with the 3D with the abelian gauge theory.
Yes, but even if it's
yeah, so basically we did this thing where first we proved something for the stack, which is kind of about like the gauge theory, and then we showed like how to impose like a stability type condition.
Yeah, like quasi maps, but kind of with a target which is a cotangent. But if you have something non-exact, I mean, I am not asking about kind of like physics meaning, but something like, you know, instead of the cotangent bundle to C, as in your last example, which is C cross C with some stratification, some skeleton, you take C star cross C star, which is a non-exact, but still symplectic. Instead of this cross of two lines, you have C stars, and so and mathematically I do not see any problem with defining I don't know, like Fukaya category or analogs of micro-local shifts. So everything is fine. Maybe it's not good for physicists, but mathematically it's fine. And I'm just curious what would be.
Yeah, so I guess the problem is that off the top of my head, I don't know. So the thing that we wanted to do is we wanted to have a theorem we could prove at the end, which was like a mirror symmetry. And I don't know the mirror to that example. So I don't know anything about that example. I don't think there's any problem, like if you were so like if you were to like follow I mean, so the dream and all of this stuff is to go back to this original definition that we gave, that I mentioned, where there was this Doan-Reshakov result about like looking at this infinite dimensional sigma model. This infinite dimensional LG model, and like looking at its A side. And so like one thing that like we've been really like trying to, so I've been talking with them a little bit, although we haven't gotten very far, also with Ben Gammage, is we've been trying to like figure out like how to like actually like do like wrapping and things, so that we can work out like on like a more general kind of target. But we haven't really gotten anywhere, and I don't think that they've done the analysis that would be necessary to handle like the non-exact case. Like I don't think anybody studied this Futter equation that I wrote down, this I ddx plus j ddy plus k ddz is zero, or is zero. I don't think anybody's like studied like enough of that analysis to have any chance of doing it in the non-exact case. Like to know like what the bubbling is and like all of that kind of.
Yeah. I mean, this analysis should be very hard. Yeah, it's better somehow to avoid it. And let me ask you another question. So, kind of a model for your 3D mirror symmetries, 2D mirror symmetry, and which is equivalence of Fukaya category and coherent shifts in mirror dual. But if your space, your X or whatever, Y, if it's complex symplectic, then you can further deform the category of coherent shifts and make it like people do. in that 3D business. Make it non-commutative, like you can deform it to D modules, for example.
Yes.
All right. And on the Fukaya side, it probably corresponds to
I think it's like this B field.
yeah, to adding the B field. Is it kind of a categorification straightforward?
Yeah, so that was, so I think that was like what I was saying. I mean, I didn't say it very well, but when I was mumbling about like why we knew that it was related to O is that basically that there's, so you have these, two, if you have a two category, there's at least two ways that you could decategorify it. One is you could take HH to the Hom spaces, or the other one is you could take HP.
Yes.
If you take an A model and you do HH, or like you the 3D A model and decategorify using HH, then you just end up with a 2D A model, possibly like with a superpotential, just using straight up. And if you take the B model and you decategorify using HH, you also just get a B model, like in complex structure I, like possibly like with like some superpotential or some support condition. And then and then there was this like fact that you're just telling me now that you can connect those things, like you can interpolate between those things basically through this Poisson bivector or B field construction, or like turning on the B field, like that lets you like move from one to the other. And basically those things are the HP, like of both the A and the B twist. Both of them, if you decategorify using the HP, you land on the DQ modules.
Okay. All right. All right.
So basically this
Yes.
thing, like like if you look at the whole like cyclic homology, it does like this deformation.
Yeah. Okay. Okay. Yeah. All right.
So that's basically the picture, is that you've got this, yeah, this pretty like this family of twists in like in like a 2D hyper-Kähler sigma model, that, yeah, like that generically they look like something like TQ modules, they look like something non-commutative, and that's like this HP from both.
Mhm. Let's see. Yeah, and actually I have one comment. Since you mentioned that you're thinking about this infrared story, and so you probably, I don't know whether you noticed, but some time ago, maybe a year or couple of years, we wrote a paper with Kapranov and Sukhanov about categorification of the algebra of infrared, which means that this Landau-Ginzburg of 2D n equal to comma 2 is on this slide. So we categorified it. So like further.
Yeah, so I've actually wanted to ask you questions about that for a while. So I know that you guys wrote down like the E3 algebra, or
yeah.
And then did you guys also like say like what kind of so you know, like in your other picture you had this direction that you have to choose in order to go from an E2 algebra to like a category.
Yes, it's still, yeah, I think it's still present, and yeah, and we should choose, yeah, we should choose the direction. Actually, it's a question even for decategorified version, because you can, I mean, direction, you means that you choose some half plane in decategorified version where you placed your webs. Yeah, and then the question is whether the answer, the category, does not depend on this choice. Well, for decategorified, for conventional, story is just this Fukaya-Seidel categories business when you change exceptional collections in yeah, and so the answer is yes. In the categorified version, it's more complicated. I'm not sure I forgot, but I think we did not prove that the corresponding perverse sober does not depend on the direction. So this I don't remember. I don't remember, but I think we didn't prove. Maybe we just mentioned it as a conjecture.
Yeah, so so I haven't had a chance to like really, like I said, we haven't gotten very far, but there's like another physicist, Hassan Khan. He's like a Greg Moore student, and so Davide and I have been like trying to think about how to do some of these because like these category O's are like massive, or like the 3D version of these categories O's like ought to be like massive things, and so they ought to work in the way that.
Yeah, that's what I meant. Yeah. Okay. More questions. Still, many people survived 2 hours.
Maybe they just like went off to.
Yeah.
Actually, I do have a question. I'll just
Okay.
Okay,
So please, yeah.
So somewhere at which page you said that the setting which is t factorial, one on the B side, on the A side and the B side, one side is Nagnot's dual. So can you explain what means factoriality?
Here.
Yes, here.
So what I mean is that if you have like a map of tori, it's like pretty easy to know like what the Langland's dual map of tori is.
So that will be on the dual group will be in the same direction. Am I right?
It should be let's see.
Should be the opposite direction.
Opposite direction, yeah. And so basically, like in one case, it's a so the specific functorality statement that we proved. The simplest example is this. We said that. So so what we wanted to do is that like there's a map. The simplest example is when you look at the map from C star just to the trivial group. And then of course that's going to be Langland's dual. Maybe this is like too dumb. And the thing that we were saying that we wanted to prove is that you had this loc 3 of BC star. And there was a functor that we had, which was like taking the invariance of the C star action. I had written S1 because it was like local system Z, so it was just topology. So anyways, there's the thing which is taking the C star invariance. But of course, if this map is P, this is the same thing as the push forward along along this map to B of a point. But of course, that's just DG cat. So things are just cat C, or sorry, no, this is 3 cat C. No, sorry, it's 2 cat. Sorry, it's supposed to be. It's a 3 category. Yeah, it's a 3 category of 2 categories. Sorry. Anyway, so the point is that that there's this push forward map, and the thing that I claimed is that was the same thing as ungaging, and that's because you have this co3 of the dual C star, and you have your P Langland's dual map, and you can do the pullback. Okay.
Actually, what I had the example was if I have a higher rank torus, algebraic torus T, and just take one character and the other one corresponding to be the co-character for the Langland's dual.
Right. So you get maps in this opposite direction. Yeah. So in general, so this is like the simplest example. This was the one that we mostly used, and then like but then you could do the same thing where if you had like 2 tori, G and H, then you'll get a map going in the opposite direction.
That's right.
Sorry, G dual, H dual. And then it's just the same. So now this thing becomes BH, BG, and now you want maps going in the same direction. So one of them has to be a push forward and the other one has to be a pullback. And then it turns out that there's more than one, but like this situation's nice enough that it doesn't matter what you do. So this is the most general statement.
Okay.
And then what I was claiming is just that this is some sort of that like this sort of equivalence is like some very stupid version of the abelian Langlands correspondence. So basically there's like different versions of Langlands, right? So there's like geometric Langlands where you prove it for about the categories attached to a surface. There's a 4-dimensional TQFT, and you can prove something about like the two categories attached to, the categories attached to a surface, the two categories attached to the circle, that's like local Langlands. And then there's like even like something you could go one level deeper down where there's like a 3-categorical version. And this is this like 3-categorical version of Langlands. And but it's actually like just ridiculously stupid. This thing literally does just come down to something like co-characters equals characters of the dual and vice versa. Like this is some like, but I think in principle, like there's this, you're supposed to be able to recover all the higher conjectures from this. So like in principle, this thing might actually know everything, but I've never worked that out. And I think that proving that would be extremely non-trivial to show that this knew everything.
Yeah, in your later example, you were looking at the C stars. Those are just the rank 1 toruses. But for the high rank, I could have many different characters and corresponding to the dual characters as I vary all the characters. And how much of the rank 1 case can determine the high rank.
So the proof was basically like no harder in rank 1 or in higher rank.
I see.
Like there was nothing, basically the rank had really nothing to do with it. And basically the way that we use this stuff in the higher rank is, I stated that there was this, more complicated equivalence that we had where I gauged any group, and I had something about this Langlands dual example. And basically we proved this just by, you check this one example, put them into this category, and then just push-pull using the functoriality, and you get it for any, like you get some statement about what it does to gauge some subtorus.
Okay, thank you.
Okay, more questions?
Yeah, can I ask one small question?
Yeah.
So previously you said we can think of the Fukaya category on S1 as local systems. And like I think about local systems on S1 as covering maps.
Sure.
And is it clear if I choose a covering space, like some n-to-1 cover of S1, which Lagrangian that corresponds to? Like, do they wind around or do we get rays?
Let's see. I'm not 100% sure. Yeah, I'm not 100% sure how to translate them to Lagrangians.
It's for T star S1.
Yeah. I'm just saying I haven't. So yeah, I just know where the universal cover goes. So the universal cover is the one that goes to the cotangent fiber.
Okay. So like, does it wind around or is it just one ray?
It's just one ray.
Okay.
But the thing is that like when you compute maps in the wrapped Fukaya category, you have to take your Lagrangian and like flow it under a Hamiltonian. And then like basically that makes it spin around. And then that's why it has an integer's worth number of self-intersections with itself. And those correspond to the points in the universal cover, or the number of fibers in the universal cover.
I see. Okay, thank you.
That's actually a good question. I should know that example, but like where just where an arbitrary covering space goes, I just don't know off the top of my head.
More questions? Well, if there are no more questions, so Justin, thanks for very interesting and inspiring talk. By the way, if you can email kind of notes which include your notes during the talk.
Yeah, I can do that.
Yeah, all right. Will be.
Yeah, I usually do that anyway. I usually like go back over and then like
yeah, all right. So
add the niceties, and I'll email you tomorrow.
Okay. All right, and you'll be the perimeter for the whole, I mean, for some time, yeah? So because,
For this year and next year, there's although because like my wife is in Florida, I like move back and forth a lot.
all right.
So basically, if you end up going, just email me and then I'll like make sure to be there. But it's just one of these things where like
Yeah, probably sometime in the spring semester, yeah.
okay, yeah. So anyway, just send me an email and then like I'll
Yeah.
just arrange to be there.
Okay, great. Okay, thank you very much. And this is the end of the seminar. Thank you.
Okay, thank you.